I think we've got our full quorum. Welcome everybody to CAM Colloquium. On a logistical note, we do not have Colloquium next week, so we'll pick up the next Colloquium after this will be on the 24th. But for today, I'm very happy that we have Katya Scheinberg talking. I actually knew about Katya from when I first started thinking about derivative-free optimization some time ago, and then kept hearing about her when I went on sabbatical at Argonne, and then I was sitting in a CAM Colloquium one day and was sort of catty-corner behind somebody who was registering for NeurIPS, it looked like, and I saw the title of the talk out of the corner of my eye and thought, I haven't met you in person, but I'll bet I know who you are, and indeed it was her. So, very interesting work on all types of things with optimization, particularly derivative-free optimization, and I think today is going to be exactly along those lines with a stochastic flavor as well.
Thank you very much. Right, so thank you for attending. So hopefully this would be, you know, a kind of, it is an overview, but it does have quite a bit of technical content. This semester, as I'm not teaching and as kind of COVID is winding down, I'm going around and giving, you know, several seminars, and so I've decided to have this one talk that would fit everything, which of course means it fits nothing, but at the same time, but hopefully it will reasonably fit here. Do feel free to stop me and, you know, like get into details. So I'll try to tell you basically a story of research that has occupied me and my colleagues for quite a few years now, but from perspective of like how we're looking at it today. All right, so I'm talking about unconstrained optimization in general, and it is unconstrained non-convex optimization where we're looking for local minima. So we're not trying to do global optimization or anything like that. Basically the traditional approach is, for example, if you want to run a gradient descent, is you assume your function is available through these things called oracles. So you might have a function value, this is zeroth order oracle, and the gradient, and that's the first order oracle. And generally you don't know anything else about your function, right? I mean, of course there are many cases when you do know way more about your function, but this is kind of the premise where what we're thinking of, okay? So this has many obviously applications, and in particular when you don't really necessarily know something about your function is because maybe it is some kind of complicated computation that computes your function, and in this case you may not have exact oracles, right? So this idea of inexact oracles have existed for a while. It's important in engineering. After all, you know, even if you have just simple computation on a computer, you may have round-off errors, right? So there's always something inexact in your oracle computations. And then what, again, traditionally you would do is you would just assume that somehow you have sufficiently small error in your oracles, and then you just apply them as if they're exact, run your algorithm, converge somewhere which hopefully is close to the actual place where you want to be. Right? So you don't worry about this inexactness too much. And in some cases, if you want to converge to the true optimal solution, the assumption would be that this error in the oracles actually goes down as you get closer to the solution in some kind of very nice predefined fashion. Okay? Right, so now, okay, this is a very basic introductory picture, but what happened in the last 10, 15 years is that there is this whole new kind of way of looking at optimization because of machine learning, specifically more deep learning and reinforcement learning, for example, which are super popular fields. So what happens there is that, so in machine learning, the gradient and the function computation is basically a training loss. And the training loss is computed over a large data set. And it is possible to compute the exact function, exact gradients. People just prefer not to do it for various reasons. In deep learning, it's the same thing because basically going a special case of machine learning, but once the deep learning came about, we started looking at data sets with 60 million data points and much more variables. So it just gets even more expensive. So it really, very rarely you would even consider computing the gradient and the function values. And finally, reinforcement learning essentially is a simulation optimization problem of some kind, where what you're optimizing is not something you can compute at all. I mean, most of the time, and so you will be just approximating it for sure. Okay, so this is just a very high-level thing that you all already know, but we're just going to keep this in mind and then question what it is that we can do. So back to the oracles. So I want to optimize a function, and I can, in principle, consider some kind of approximation of the value of the function that I may need to use in my algorithm, some sort of an estimate of the gradient, and maybe even a Hessian if I'm trying to use second-order methods. Okay, so I have these stochastic oracles. And unlike deterministic oracles, it is all of a sudden very unclear what it is that we can claim about these oracles. Like, what can we say? I mean, are they, you know, it's an approximation of the true value, but what other properties do they have, and what kind of properties are we going to use? Because depending on the algorithm, or depending on the properties, some algorithms would work and some would not. So your typical assumption is that these oracles are unbiased. Right? So I'm going to use this notation here quite a lot. It's maybe a lot of notation, but basically, instead of the true function phi, I'm going to use the approximation f. It's at point x with some kind of randomness here. This psi 0 is a randomness. Same thing here. G represents my gradient, G for gradient, H for Hessian, right? And then I may have different types of randomness that produces these things. But in the typical assumption is that these are all unbiased estimators. Okay, and the question is that enough? Another assumption that is typical in, say, empirical risk minimization is that not only these are really unbiased estimators, they really all come from kind of the same, the randomness is shared in a sense that if I compute an estimator, so I pick some kind of random, think batch, right, mini batch, some data sample. On the data sample I can compute my loss, right, and then I can differentiate that loss, and I'll get the gradient estimate. I can differentiate twice and get a Hessian estimate. So this is what is very often assumed in machine learning. And I'm going to, in some sense, argue through some examples that, first of all, just assuming that your oracles are unbiased is completely not informative in terms of your algorithmic performance. And sometimes it's also not true because there are many other cases where you would have biased, slightly biased estimates or oracles, and then what do you do then? You know, how can an algorithm handle this? And then this is also often not true. I'll give you examples of this, that just because you have some kind of a zeroth order oracle does not actually automatically give you the first order oracle. So you have to work on that to some degree. Okay, so the kind of the goal, so this is the introduction. And the goal of the work initially was, okay, so let us not start with some kind of standard oracles, stochastic or not. Let us take the algorithms that we kind of know and love from, well, some of us, from the past, line search, trust region, cubically regularized Newton, and I'll tell you what it is if you haven't seen it. It's just nice, theoretically nice algorithm, which is similar to the other two. But the other two are very, very standard algorithms in optimization. So let's take these algorithms and let's try to relax them as much as possible, the assumption on the oracles. What it is that they need from the function values, gradients, and Hessians, and still retain their convergence properties. Okay, then define these relaxed oracles in the most general way that we can, and then perform the analysis. So first of all, perform the complexity analysis, and then perform complexity analysis, and then total complexity. I'll get, on with the details about this later. And the idea here would be that if we develop such algorithms and then we develop this general definition of oracles, then we can kind of mix and match settings where the oracle may come from something, some particular application that you have in mind, and then the algorithm will have some requirements on that oracle, and then you will decide on basically, can I make my oracle fit into these algorithms, and then I can combine them, and they will be readily, the theory will be readily available for you. Okay? Other questions so far? Okay, right. So now, why line search? In case some of you still don't either know or believe why we should use line search, or if we can. And in the end of this talk, I will kind of talk about what it seems like apparent to us now that we understand when line search is a good idea in stochastic optimization. But anyway, so why do we use line search? So what is line search? Line search is a way to determine the step size parameter when you're doing, say, gradient descent. So we know that if we're doing gradient descent and the function is L smooth, then a certain fixed size step size, alpha k1 divided by 1 over L, will always work and the algorithm will converge. This is something you would learn in any gradient descent basic introductory lecture. However, as soon as you don't get the gradient exactly, but you get something else, then this whole thing becomes more complicated because it's no longer 1 over L. There could be a fixed step size parameter that would work, but you don't know what it is. And even in the exact case, 1 over L is the Lipschitz constant of the gradient. It is very well known that this is a pessimistic bound, also not known. And so it basically creates all kinds of issues. And in stochastic optimization, when this G is stochastic, then you really don't know what step sizes to take, and the usual way to deal with it is hand-tune your step size parameter for specific data sets. Okay? Trust region is basically just a different method that also adaptively selects the step size. And so the idea here, what I'm trying to convince you, is that adaptively selecting step size will be much better. So here you can see that it works a lot faster if you actually are trying to pick the step size in an optimal way. Now, how does this work? Okay, so this is a very general framework, which I will specify later into these 3 categories: line search, trust region, cubically regularized. But it's kind of nice to think about these adaptive optimization methods in this one uniform way. So what do? So at every iteration, we're computing a model of the objective function. So we don't know the objective function, we're computing its model. How do we compute its model? In the traditional deterministic optimization, it's a Taylor series model. First or second order, that's what it is. You just use Taylor series. And everything that I'm going to talk about today is inspired in some sense by Taylor series. Like, that's all we do in continuous optimization. We don't know anything else. But now I have random models, right? Because I don't have exact gradients, I don't have exact function values, I have some kind of approximations that are random, so I have a random model. Okay. Now this model, I'm hoping, is a good representation of my function. It may or may not be. If I believe it's a good representation of my function, I will try to minimize that model somehow, and that should give me, the step. Proposed step. Now, the step is going to be computed based on the step size parameter. So the step size parameter is basically dictating how aggressive I should be. And it affects, you'll see in specific cases. So if I want to be more aggressive, alpha k should be larger. If I want to be less aggressive and more cautious with my steps, it should be smaller. But I computed that step, depending on whatever alpha k was, and now I'm going to check if actually that step is good for me. So which means I'm going to compute the function estimates at the current iterate and at the new iterate, and I'm going to compare them, and I'm going to check if their difference, is sufficiently reasonably small, basically, if I've achieved degrees, right, if I make progress. Okay, and if yes, I will accept the step, and I will be more aggressive next time. I will increase the step size. If no, I will reject the step, I'll stay where I am, I will decrease the step size. In your typical algorithms like line search or whatever, if I am not accepting the step and I don't move, I'm going to decrease the step size, and I'm not going to recompute the new model. I'm not going to compute the gradient again because I know my gradient is accurate. But here, because the models are random, I have to actually recompute things every time. Because otherwise I might get stuck with a really bad direction, which may be uphill. Okay, so this is key difference with deterministic methods, is that we are going to recompute things. And another key difference is that I will always increase my step size and try to be more aggressive if I accept the step. So we will see where it's important in the analysis. Yeah?
I wonder, why do you compare the reduction of function value to the reduction of local model here, rather than compare it with the step size?
So it is actually the same thing, in some sense, as you will see.
It's a linear model.
So it depends, right? If it's a linear model, so this is exactly, let's specify it to the methods. So you know line search, and in line search it is basically this thing. So you have a model, which could be a quadratic model, so HK can be anything positive definite, but also can be identity. If it's identity, this is nothing but gradient descent with the, well pseudo gradient descent, but the descent along the direction negative g. And the step size is really here, but you can just write it this way. So basically taking this step, as you would know in gradient descent, is equivalent to minimizing this model exactly. Okay? And indeed, the Armijo condition is basically saying I'm going to check that the decrease is proportional, well, is at least this. This R thing is something we need because of inexactness in our function values. I will not talk about it much, but just it's important that these conditions are a little bit relaxed in general. But, so this is exactly, like, you are comparing, essentially what you're doing here is you are comparing the decrease to the decrease in the model. It's just here it's very explicit. The decrease in the model is this, specifically. So we can write it that way. But when we're actually talking about trust region, it becomes more general. So in the trust region method, you essentially have now quadratic model where H does not have to be positive definite. And this is the purpose of trust regions in various ways, is that you can then optimize. So if you wanted to do line search, you would need to minimize this quadratic, but this quadratic may be indefinite, therefore the minimum might be at negative infinity, so you cannot do that. So trust region comes in by saying, I'm going to minimize this model in a ball of radius alpha. Okay? The difference, the key difference really with the line search is that your step size is explicitly controlled by alpha, so you cannot possibly make a step larger than alpha k. Whereas in line search, it's different because you are taking the step alpha k times the gradient. So if the gradient is somehow very large or very small, that affects your step size. So there are differences, but otherwise it's a similar thing. And again, you check the convergence. Improvement in the function. Okay, and here I'm listing all the papers that have analyzed various conditions, various versions of this and the stochastic oracles of different types. Okay, and cubical regularized Newton, if you haven't seen it, so it's kind of similar to trust region, except for HK is assumed to be real. I mean, it only is useful, this method, is if HK is really close to the Hessian. And in that case, what you do is, instead of minimizing this function in a ball of radius alpha k, you add the cubic term, that's why it's called cubically regularized Newton, which essentially, if alpha k becomes small, then this term dominates and you don't make large steps, right? Because you're going to minimize this model, and this is a huge term that doesn't let you take large steps. if alpha k is small, then this is not important, and then you're taking larger steps. So again, alpha k controls how far you're going to go, just a little bit more implicitly. And the cool thing about this method is that it has optimal convergence rates compared to the other ones. So it just converges faster in theory. In practice, it's not any better than the trust-region four-line structure. But we need to include it because, you know, it has better convergence. Okay, any questions on this? Or any? Okay, right, so on all of these papers, you seem like I listed a bunch of papers, right? So in all of these papers, in one way or another, we had to make assumptions on the accuracy of our estimates to be able to show convergence, right? And so these assumptions are, loosely speaking, that's very loosely speaking, are like this. That if you want a first order convergence, so you have a first order method, okay, so ignore this line because it's actually stupid, but so if you want the first order convergence, then the accuracy of your function values have to be proportional to the step that you're taking squared, right? So the step that you're taking does depend on your function, so that's why it's loosely speaking. But in the beginning of your method, you're making large steps and you're progressing fast, so you don't need very accurate function estimates. And as you go closer to the solution, you need more accurate function estimates, right? With a gradient, you basically need the accuracy that's proportional to the step size, to, you know, length of the step size. And if you want second order convergence, then you want this to be, you know, cubic, basically, of the step size length, and the gradient should be quadratic, and the Hessian should be to, you know, up to degree 1. These are essentially coming from Taylor expansions. That's what it is. Right? So Taylor expansions, this would be true in a ball of radius S, and we're just saying that, okay, we're requiring this condition in the center, so the Taylor series still works. Okay? But the important thing is that we don't require this to hold all the time, because otherwise we will not have stochastic situation, right? We only require this to hold with probability P. Okay, and then the question is, can we actually analyze such a method? Yeah.
Can I ask a very basic question?
Yes.
In the first order methods, for example,
Yeah.
why do you care about the accuracy of the function computation? Because all you're going to use is the direction.
No, but I'm doing these adaptive methods where I compute function to decide whether I take a step or not. Right, so this is very important. Right, that's the only time I'm using function values. I'm not using them to compute the models at all. I don't care about them for the models, but I do need them for the for the adaptiveness, right? Okay, so so now I'm going to give this very convoluted definition, which we're kind of trying to push. Very general definition of stochastic oracles. The three things are the same, except for zeros, first and second order, so let's just focus on the thing in the middle here. So this is stochastic gradient oracle, which is very different. I mean, it's not very different. I'll argue that it encompasses many settings that we know, and then some. So it's more general, but like it looks weird. So, okay, so let's think about it for a second. What does it say? So I'm given a pair of numbers. The first one is going to be accuracy, and the second one is going to be reliability. So accuracy is mu, whatever. Reliability is p, it's probability. So for any given pair, my oracle is able to deliver approximation of the gradient such that it is this accurate with this probability. Okay? So, right. So now I'm saying that my oracle, wherever it comes from, is implementable over a set of pairs. Okay? So what does it mean? For example, it's possible for me to somehow produce a gradient estimate that is accurate up to, say, 0.01 with probability at least half. That means it's implementable over that pair, 0.01 and half. Now, clearly, it's also going to be implementable for anything bigger than 0.1, right? And anything smaller than probability 1/2, because if I can achieve this accuracy with this reliability, I can achieve the worst result. But there may be a cost associated with producing this oracle, and so the cost actually can vary. If I don't have to be as reliable or as accurate, I might be able to achieve this at a lower cost. And this is important because it will come into the final complexity, right? The total complexity. Okay. So now we actually can compare different oracles for various reasons. Okay, so let me try to explain. So there is a requirement on the oracle that the algorithm imposes. And then there are different costs of the oracle that come from where they come from, the application, right? The way I'm computing the gradients. I'm going to leave this application aside for a second, and I'm going to talk about the requirements of the oracles. The requirements are whether they're implementable over a particular set, okay? And now I can compare different methods in terms of what their requirements are. Okay, I'm not going to really compare the methods here because take some time, but basically some of these papers or many of these papers that are listed before, they work for different types of oracles. Here I'm just gonna give you an idea how nice now we can compare things. So what is this? What is this set? This is the set. So these A's are actually should be U's. Sorry. So this set says that I'm including 0.01. Which means that in principle, I should be able to deliver exact oracle with probability 1. So I should be able to compute my function. Maybe I don't want to all the time, but I should be able to do it. In machine learning, there are methods that actually do that. Like SVRG is such a method. Occasionally computes the entire gradient, but at the other times it does not. So it is possible to do this, even if you don't want to do it all the time. This is a situation where I'm allowing noise in the function values that is not reducible. So I'm allowing to always have an error. This is not an unbiased estimator anymore. There's a bias in my estimator. Like there's always an error. I cannot do better than this accuracy. But I can deliver it with probability 1. Okay, so this is bounded noise. It very often happens in various inexact computations. This is kind of the other way around. Well, this one is the other way around. I said I can deliver exact gradient, but only with some probability, and I don't know what happens otherwise. I can compute the exact gradients, but then maybe I have some corrupt data with some probability, and then I don't know what happens. All garbage. This is the case where I can deliver arbitrarily accurate estimate with some probability, but not the exact one. So there's like the zero line is meant to be taken out. And okay, this is the least, sort of the weakest, in some sense, oracle, weakest assumption of the oracle, that I have noise and I can deliver them with only with some probability, and this is another kind of nice assumption. With I have noise, I might exceed this noise, so not like here. I may not deliver it with probability 1, but the probability gets higher as the noise goes larger. Okay, any questions about this? So all these things have been used in papers in the past, and now we can nicely compare them visually. Right. So now let's talk about specific oracles. So this should be hopefully familiar to some degree. Expected risk minimization. I have a loss function, I have a data set, I pull data from the data set, I put them in a mini batch, I average the loss function, I get my function estimate, I average the gradient, I get my gradient estimate. Right? Very standard stuff. Okay. So under basic assumptions that my loss, so this is where it's important, right? So I said like we assume that we have unbiased estimators, and this is a usual assumption, but it's not enough. What you really need to know or assume as well is the variance, right, of your estimators. So if your variance is something specific, say bounded, well, it doesn't have to be specific, but it's bounded. Variance is bounded. This is the variance of the gradient. This is the variance of the function. Then, simply by just averaging sufficient number of samples, and this comes from Chebyshev inequality, nothing new here, I can guarantee my oracle. So the exact numbers we'll come back to, doesn't matter, but just think about it, right? So if I have an unbiased estimator, and I want some accuracy with some reliability, I'll just use Chebyshev inequality and sample sufficient number, right? So clearly, if I need more accurate oracle, I will need to sample more, and therefore my oracle cost is going to change, right? My more accurate or more reliable oracle. Okay, any questions about this, how it fits into the framework? Okay. So now there's a different situation where we're doing expected risk minimization with the L0 loss. So it's basically the true loss, right? The expectation of the error. This is just an example. There are many other examples that are maybe more reasonable, but I like this example. So if you're trying to, so instead of say logistic loss or some other nice smooth L2 loss or whatever, you try to actually optimize what you really care about, the probability of making an error, then that function in expectation, what you're really trying to optimize, can be smooth. Not always, but often it would be a very nice smooth function. However, any finite sample approximation is going to be this stepwise function, right? Which is where we see that the probability, the function estimates that we can compute. So this is basically the stepwise function is our f, and the smooth function is our phi. And we can see that the function itself, f, is a pretty good approximation of phi. But the gradient of f is completely useless. So we need another way of computing gradients, right? So we have a zeroth order oracle, but we don't have the first order oracle here. But actually we do. This is where we go back to derivative-free optimization. So this is derivative-free optimization is you know, has many different ways of approximating gradients. And in many cases, that's essentially what we do. We approximate gradients. We just don't approximate them by differentiating. We approximate them by some other means. And this is one very basic way of doing it, is finite differences. Probably everybody knows how to do this, right? So you have function values, you take finite differences, and then you have a gradient approximation. Except, if you have noise in your function values, and you kind of imagine already even from this picture. So if I try to use finite differences, I have to make sure that my step size is kind of large, right? Otherwise I'll also get garbage. If I take the finite differences with a very small step size, I'm not going to get any information. And this is reflected in this very simple result that basically says that if my noise in the function values is bounded by some number, let's say epsilon f, then I will have the gradient estimate that is bounded. This is 4 with finite differences, central finite differences. Doesn't matter, let's focus on this. Basically, it's bounded by this. H is my finite difference step. Here, if I reduce H, this term goes down, this term goes up. Right? If I increase H, this term goes down, this one goes up. So I have to find some kind of golden middle. And if I knew these values, I know exactly what I need. Otherwise, I have to estimate. But the point is that I will have an estimate that is as good, essentially, as my noise. In fact, it will be square root of that noise. So my first order oracle is going to be as accurate as the square root of my zeroth order oracle, which is precisely what the Taylor series kind of behavior requires of me. So it's all kind of works well. And yeah, and I have a bias here. I cannot make this as small as I want. So this is a biased first order oracle with hopefully small bias. If the bias is, I mean, if this error is very large, then I cannot do much. But I can And I can analyze these things. That fits into my oracle definition. It gives me a cost of computing this oracle and so on and so forth. So I can fit it right in and then just, you know, plug it into the theory. Okay? Any questions about this? Okay, right. So, deep breath. Still have time. Right. Yes. So now I'm going to basically give you some idea about how, under these assumptions on the oracles, right, under this kind of oracles that just deliver some accuracy with some probability, how do we analyze such methods? What's behind the analysis? Just, you know, some idea. Okay, so, oh, actually, sorry. Before that, I mean, I'll get there in a second, right? So, there are two things to the analysis, rather. The first one is the iteration complexity. So, how many iterations would the algorithm need to converge? Okay, we'll talk about that. And another one is this oracle complexity. So, oracles, as you can see, so this is an example of the use of an oracle in a trust region method, for example, analyzed in this paper. So alpha is our trust region radius. It goes up and down. It gets multiplied by something, divided by something, right? It changes all the time. And the requirement is that the first order oracle, zeroth order oracle, sorry, is proportional to something, some constant times alpha squared. And this is something times alpha, right? This was exactly like proportional to the step size squared or the step size by itself. But only with probability P0 or P1. So this is how it's used. And the point of this slide is to say that if we're, for example, using empirical risk minimization or empirical loss minimization, that means that we have to sample sufficiently large number of samples depending on this alpha, okay? And this alpha, so basically if this alpha goes to 0, then this will explode and we don't have a bound. So I'm going to basically tell you about how, and like why would alpha go to 0, why would alpha not go to 0? So this is basically a discussion. Let me actually see if this is, right. Okay, so we have the algorithmic framework, we know what we want for it to work, and now we're going to try to talk about how we can analyze this. Okay, so now let me explain what happens and where the, what's happened with the analysis. So this is a deterministic algorithm. So I have, red is my function, blue is my first order model, and I essentially take a step size, let's say it's, you know, minimize whatever, it's trust tree. I take a step size of particular size, right? And if it's a step size that is somehow in agreement with the model, I'll take it and continue, maybe more aggressively. And if this step size is somehow taking me too far, see that the function curves fast, so clearly I've stepped too far. I don't want to go that way. I should cut my step, right? These are the only two things that can happen. And this is why we know that the step size of a sufficiently small length, like 1 over L, is going to be always accepted. Okay? Did I lose people already? I know, low on energy. But this is basic, right? So step size 1 over L. In deterministic optimization always works. What does it mean? That whenever I'm using deterministic adaptive optimization, I know that if I cut my step size and increase it and cut it and increase it, eventually, so it cannot go to 0, basically. That's the point. It can never go to 0 because when it's small enough, I always accept my step. This is how all the analysis of deterministic methods work. In the worst case, my step size is going to be this small. Every time it happens to be this small, I'll take a step, my function will decrease, and I cannot do this too many times, therefore, complexity bound. Okay, this is how it works. Now, we now have something that is not necessarily good. So this is the situation where things are inexact but accurate enough. So I don't have exact gradient here. I don't have exact function values, but the accuracy is sufficient. And I'll still take my step and everything, and my function will decrease, and I can kind of analyze this, right? And this is a nice situation. So now I have a different situation. What happens here? My function is in red, right? My function estimates are pretty good. Blue is my model, like basically gradient estimation, and my gradient is completely wrong. It's pointing in the wrong direction. So what will happen here, I will try to go here, take the step, so I minimize my model, this is my step. I'll compute function values, the function values say, no, don't go there, because function is increasing. So I will miss an opportunity to take the step, I will have a wasted iteration, but I will not move anywhere. But I will decrease my step size. So now I'm going to decrease my step size because I was wrong in my model. Here is another situation where I'll decrease my step size because I'm wrong in the function values. My model is fine, function values are bad. I will try to take a step, but my function values will lie to me and say, don't go there. So I will not go there, I'll decrease my step size again, I wasted iteration again, step size can reduce. And finally, this is a different situation which can cause trouble, where I will take the step because basically both the model and the function values have cheated me. So I'll take a step, I will increase my step size, so this is not when the step size goes to 0, but I also am doing something wrong here because I'm actually increasing my function value, so I have to take that into account. Okay, so these all things have to be taken into account, and how do we do that? Essentially by just hoping, and not hoping, but like analyzing things carefully and making sure that the first situation happens sufficiently frequently and the decrease on this situation is sufficiently large that whatever else happens on these other iterations is not going to produce too much damage, and that we're overall tend to converge. So there is some complicated kind of martingale process going on. And the key thing that I want to emphasize here in this talk for this martingale process is that basically, so we just seen that the step size parameter, unlike deterministic methods, can go to 0. Right? So it can arbitrarily, because you make mistakes, it can decrease and decrease and decrease and decrease. The key property in all these methods is that when it is sufficiently small, so remember in deterministic optimization, it cannot go below some threshold, it cannot get smaller. Here, there's a threshold, and so that's basically complexity analysis condition. There's a threshold that as soon as you're below it, you tend to go up. So you're more likely to have a successful step than not successful. So that's the behavior. And every time you have a successful step, then the function decreases by some amount. And okay, yeah, if you have a good model. So this is basically the behavior of this alpha k. So when it's large enough, it does something, I don't care. When it's below some threshold, it starts behaving. It is a random walk, it's always a random walk, but now I know that this random walk has this upward drift. And this is a log of alpha, because otherwise this is geometry, right? So there's this random walk that we can analyze, and we can basically, and this is why everything works, basically, in these methods. That's the key property. So while this alpha k, again, can go, in principle, arbitrarily close to 0, it tends to return to this threshold value. Yeah.
Does this hold in kind of, this is analysis is mostly for the case where you have like a stochastic problem where the gradient can be exact with some probability. But
not exact, no. It doesn't have to be exact. Sufficiently accurate, as I said. Like,
okay, but can your accuracy be bounded away? Like you have one example where the accuracy was bounded away. Does
right,
it still
okay,
hold?
yeah, good, right. Yes, so in all cases when you cannot have accuracy better than blah, what we analyze is that we can have convergence properties up to neighborhood of the
Because that's the threshold on the line.
Exactly.
Okay.
So yeah, well, there's exactly that, but also, but basically, yeah, you can converge up to epsilon accuracy, where epsilon is bounded below by, you know, the error in the gradient, the error in the, exactly.
Okay.
So it totally extends like so that's why it's so general. As soon as the error goes to 0, if it's 0, then
Yeah.
you converge to the optimal solution, otherwise it's somewhere nearby. Yeah, right. Okay. So this is the key thing, that we can tolerate arbitrarily kind of bad errors from time to time with some probability, and then we can tolerate small errors just in terms of converging not exactly to the solution. Okay, so this is, you know, that. So this is summary that is not, you know, it's important because it's quite a few years of work and several papers. But the key thing here is that exactly under these conditions and with this kind of analysis, we basically show that under different, so these are the pictorially showing you that these papers are using different type of oracle assumptions. And once you use these different type of oracle assumptions, then you can have convergence in iterations, in terms of number of iterations, which actually match complexity of the deterministic methods. So we are not losing anything, well, except for constants, because, you know, we do lose something in the constant depending on the probability of good models and so on. But otherwise, we basically have deterministic like convergence rates of these methods or various cases under different conditions of the oracles. Okay, and yeah, this is precisely where the condition convergence epsilon up to is dependent on the best possible accuracy you can achieve. Okay. Right. So now the final thing, which is, you know, kind of the nice wrap up to this whole story, which is, you know, the paper we're currently finalizing for submission with Billy and Milan here, is the total complexity. So what do we need for total complexity? Remember, we have iteration complexity, and now the complexity of each oracle may depend on the accuracy that we want. So these oracles are actually more or less costly depending on what happens in the algorithm. And this has been, you know, kind of a difficulty with these methods for a while. So specifically, again, for the trust region, for example, we have this requirement on the gradient, this requirement on the function values, and to deliver this, we need to sample this much. And this alpha k here is the step size parameter, right, which in principle can go to 0. Right, so now we need to analyze, so for analysis of complexity, iteration complexity, we needed to make sure that alpha k occasionally returns to some value on the threshold. Now it's different. Now we want to analyze the lower bound on alpha k in general, like that it will never go below something. Okay? So otherwise we cannot bound the total complexity of the oracles. So again, we have these dynamics, right? So it's a random walk. Above it, we don't care. Below this threshold, it's a random walk. So now if we have a random walk with reflection, can we say something about it getting, you know, arbitrarily negative, let's say, with some probability? What's the probability of it reaching negative million, right? Or negative whatever, 10 to 9, or negative 5? Can we say something about it? So this is the result that is pretty complicated. I thought initially it will be an easy thing, but it turned out not, and Milan really worked hard on this, and this result is really, it's not that comprehensible. But then you can kind of stare at it and figure out a few things. So first of all, here is what the theoretical bounds are, depending on the gamma. Gamma is the parameter by which it's important here, by which you update your alpha, your step size. So how quickly you increase it or decrease it. So depending on the gamma, so this is the lower bound, the theoretical one. This is actually a simulation of a random walk. So this is actually what happens in practice. You can see that while these bounds are kind of pessimistic, they're not exactly super pessimistic. And the worst thing that you can see here, in my opinion, is that, I mean, as you run your algorithm longer, then the lower bound gets smaller. So if you want to run your algorithm for a very long time, you will be getting smaller and smaller alphas, occasionally. Not all the time, obviously, right? But occasionally. So this is a very pessimistic total complexity analysis that we're doing so far, but you know, at least it's something. And the nice thing about it is that, okay, so this is a lower bound on the alpha. If p goes to 1, so that is, your method is deterministic, then actually that lower bound goes to exactly the lower bound for the deterministic method. So think about it 1 over L, basically. That's what it is. So you recover a deterministic result, which means that we're doing something right. If gamma goes to 1, which means we're not adapting algorithm much, alpha much, so we're basically doing fixed step size, then the minimum will be that fixed step size, which it should be. So it works out well as well. Then, you know, if you fix gamma something, for example, this probability of success, this is fixed gamma, then you get some kind of decrease in your step size, which is square root 1 over square root of k, which Billy and Milan got excited because it looks like stochastic gradient descent, but we're not really doing stochastic gradient descent, so I don't know what to do with this information. But the best thing is that this result eventually gave them the idea that they can have gamma selected now depending on how far you want to go. So if I know in advance how far my algorithm will run, how long it will run, then I can choose gamma accordingly carefully so that the lower bound on my step size is going to be fixed. Okay, so if I want to decide on basically, so if I want to kind of guarantee some nice behavior of the total complexity, I want the lower bound on my step size parameter fixed, and I can achieve that by choosing the appropriate gamma. And interestingly enough, it actually works really quite consistent with practice. There are some numbers here that are thrown together, but basically it says, like, if I want to run an algorithm up to some accuracy, I know that my number of iterations should be proportional to 1 over epsilon squared, if I'm generally working on a non-convex case, and that will give me the gamma, and the gamma should be something relatively close to 1. And that's why we observed this in practice in these stochastic methods that for trust region initially we observed it, and then for line search, you really want to be quite careful about how you decrease and increase your step size, especially decrease. So you want to be, because otherwise it will go down to small, and then yeah, things will go wrong. Okay, and so this is the final wrap-up. So the total complexity for sample averaging or empirical risk minimization is essentially this. Because of all these things that I just said, putting them together, it turns out that the algorithm that we would run, for example, on the trust region case, and in other cases too, I didn't go into this, will be this. So what is this? This is the variance of the gradient estimates, individual gradient estimates of my loss function. This is epsilon that I want to achieve. This is the variance in my function values. This is, again, epsilon. And this piece here is the best you can do for any stochastic gradient method. This is the lower bound. This is the best. You cannot do better than this. Okay, so we're really doing well in this sense. Here, all of a sudden, we're not, right? Because this is 1 over epsilon to the 6th, which is a lot worse than 1 over epsilon to the 4th. However, I claim that in many cases, and this is, again, people kind of agree with that statement, that the variance of the function values often, especially in things like deep neural nets, is much smaller than the variance in the gradients. gradients are much more volatile, and that's because of Lipschitz constants and things like this, than the actual function values. So if this is quite a bit smaller than this, then this term all of a sudden is not the dominating term, and then your line search would work. We need this red part for the line, well, not just line search, but for the function values. Function values need to be accurate, more accurate. So if they happen to be more accurate already, then with the same batch size, everything will work. If they're not accurate, then you should not be doing adaptive methods, and you should forget about function values and just do whatever stochastic rate usually does, or hand treat. And that's it. I have some example here, but I'll skip that. And basically, in conclusion is that we kind of have this framework, which is quite general. We have these general oracles, and I would be very happy if somebody here will come to me one day and say, oh, I have this oracle, I didn't know what algorithm to use for it, or how to match it into the theory, let's see how it fits into your framework. And that's kind of what I would like to be working on in the near future. And thank you.
A few minutes for questions.
So you have a 1 over alpha to the 4th dependence, and for some problems we've run into, it's like you can't take 1 over alpha to the 4th samples.
Yeah.
I don't know, we've come up with like some ideas on how to reduce that, but with like Stefan and Jeff, but I was wondering if you had any thoughts on how to break down that dependence, something like a little bit more tractable.
Yeah, well, I mean, in theory, you cannot presumably. So 1 over alpha to the 4th. You're talking about the function value.
Yeah, exactly.
Yeah. Yeah. So I mean, in some numerical experiments, we just forgot about the alpha. We just took like large enough sample, and it seems to be working. So again, it really depends on this, I guess. Otherwise, if you're hitting a limit on your accuracy, that is essentially like having a bias in the function values, which will dictate exactly what kind of accuracy you can achieve in terms of just overall complexity. How to improve this? So Luis Vicente telling me that he can do cube there somehow, but I think he's doing something a little different, so I'm not sure it will fit. But yeah, there, I don't know, quasi Monte Carlo methods, I don't know, some other stuff. I mean, I would love to see, yeah. If you're just averaging, can you do better than this? I don't know.
Are there any lower bounds on these batch sizes saying that if you do less than this, you'll, or examples where you probably do, divert, go to somewhere else? Or does it make sense in this framework?
I mean, you can always come up with examples when you definitely diverge, right? I mean, lower bound will depend on what kind of data it looks like, right? I mean, if you happen to have a huge data set with every point is the same, right? Then there's no lower bound because every single data point will be the correct one. So you need some kind of, but I mean, yeah, if your variance is large and if you don't pick enough samples, then it will definitely diverge, right? I mean, I don't know what you mean by examples. Particular examples or?
We'll take those.
I mean, the fact that, right, that the final thing is 1 over epsilon to the 4th, this is known to be the lower bound on total complexity for any stochastic method. It's that. In terms of samples.
So you've been talking sort of about the complexity for local convergence. Of course, one of the things that people tell all sorts of funny stories about is the global exploration properties of these. If you've got some non-convex thing, have you looked at sort of the analysis beyond very local convergence? Like if you have some measure of local convexity, probability that you will stay within this bowl over a period of time, or is it all right now at the level of you have to start close enough?
So you don't, I mean, well, okay, yeah, right, so for these things, you don't need to start anywhere, but you'll converge to a, whatever, first or second order stationary point, right, for these methods. If it's convex, there's conversion, but yeah, the fact, I mean, given that you have stochasticity, you could jump out of anything and end up somewhere else, in some sense, and yeah, I don't know. I'd say that, like, if you have this kind of behavior, right, on the function, then you can treat it as noise and talk about that sort of convergence, but yeah, but I think it would be very, very different techniques at the end.
So we are at time. So if there's no further questions, let's thank Katya again.